All right, let's talk about concurrency bugs. Concurrency primitives provide a good way to control concurrent executions, but as a downside, it sometimes leads to very unintuitive bugs. So in this lecture, we talk about two different types of bugs, deadlock bugs and non-deadlock bugs. So let's talk about deadlock first. So as this slide says, synchronization is like a live gun. It provides a useful way to control concurrent executions, but sometimes it shoots ourselves in the foot. So we have to be very careful to incorrect use of synchronization that blocking all processes. So in deadlock, refer to the situation where one process tries to access a resource that other process hold and vice versa. So eventually no one make up progress. So never making progress. I mentioned this problem before, right? So when program having two important properties in terms of evaluating concurrencies, and one is safety, and the other one is liveness. So safety and liveness are different type of bugs. We talk about problems of safety and liveness. So deadlock is related to liveness, where no one making progress. So it violating liveness guarantee. So this lecture, we will formally look at deadlock situation. So looking at definition and necessary conditions for incurring deadlock. And we analyzed representation of deadlock conditions, three representative conditions incurring the deadlock and approaches dealing with deadlock. So how to avoid it and how to actually recover deadlock. So for deadlock, deadlock has related to resource, a limited resource. If resource is unlimited, we may have using many ways to avoid deadlock, but resource is limited. So there's some kind of a contention to using the resource. The resource I'm referring to CPU, disk, memory, log. So in the lecture, I want to generalize every resources, but usually in the synchronization concurrency, we focus on the log. So to holding a resource, there are two types of way to hold the resource: preemptive way, non-preemptive way. So preemptive way is the operating system take away anytime if it's necessary, and non-preemptive is most resource always leaving with a holding thread. So two types of holding resource, and for this resource, deadlock cause this starvation. So the consequence of deadlock is that all the threads wait infinitely. So the system doesn't make a progress, causing a starvation. Typically, this deadlock is created by this circular waiting property of resources. Let's take a look at it. So I'll give you a very popular example of causing deadlock. So there are two threads holding a lock. Okay, and the thread A holding had the code sequence of this one, and thread B having this code sequence of one. So let's two threads are running into two different cores. So thread one first start its execution and holding a lock. So thread A is like a lock holder of lock one, and then before thread A holding a lock two, thread B preceded and holding a lock. So this is sequence of one, first sequence, and this is second sequence. After that, thread A 1, 2 holding a lock, but lock 2 is already held by thread B, so wait for the resource. Wait for. Likewise, thread B 1, 2 holding a lock 1, but lock already held by thread A, so also wait for lock. So this circular waiting, so thread A waiting for B, thread B waiting for A. So these circular relations causing deadlock. Okay, so these are most common use cases, most common example of deadlock. So, but just by looking at this example, you may say, "Oh, this is intuitive." So, just kind of changing the log order so you can easily identify deadlock. But in practice, you have like 1,000 of line, and you hold the log at some point and call a lot of functions, and then holding a log 2, and the other function called the code path holding a log A and log B, and then you're holding a log 2 at some point, and there are some kind of lots of functions executed there at log 1. So if you can boil down to this simple code snippet of log sequence order, but in practice this ordering is unintuitive. So this is the most common mistake in programmers to holding the log this sequence or different log order causing deadlock. Okay, so from this example, we can actually formalize 3 important necessary conditions. So first, as I say, circular waiting. So there are a set of waiting threads, each of thread waiting for resource held by another thread. So there's a circular waiting. And the other one is wait while holding. So this is how the lock works, right? So when someone actually holding a lock, the other thread has to wait until the other thread releases the lock. So this is kind of a general kind of principle for deadlock. So any resource, but intuitively, lock actually satisfy this condition: wait while holding a lock, and no preemption. So no preemption means that once a thread requires resource holding a lock, its ownership cannot be forcibly revoked by other guys, operating system or other thread, until the thread voluntarily releases it. There's no preemption. As I say, these are necessary conditions. What does it mean? Is that to prevent deadlock, we can eliminate only one condition, then deadlock never happen. Okay, so if you can eliminate circular waiting, then there's no deadlock happen. And if you can eliminate hold and wait condition, then deadlock doesn't happen. Also, likewise, no preemption. If you can allows preemption, then no deadlock happen. Okay, so that's kind of key for avoiding the deadlock. So we will discuss later how to avoid deadlock by kind of eliminating each condition one by one. So to prevent deadlock, there are 2 possible approaches: proactive way and reactive way. Proactive way is that like this word says, make the condition does not occur. Okay, so proactive is kind of defensive programming, where there are some principles and programming practice to avoiding one of these conditions. Reactive way is that when deadlock happens, let the deadlock happen, and then do some corrective action by kind of break the conditions forcefully. Reactive is usually hard to implement. The proactive is a more popular way. So defensive programming for avoiding the deadlock is common in practice. So let's take a look at the first condition. So first way to avoid deadlock is most popular way is avoiding the circular waiting. Okay, so as I say, this lock problem, I explained is violating the lock holding order. So circular waiting is kind of avoided, is eliminated by holding a specific sequence of lock. So in every thread, when holding a lock, there is a fixed order. So thread A and thread B always holding a lock in increasing the sequence. Okay, so by having a lock this way, thread A holding a lock and thread B cannot holding a lock too, because it's require holding a lock A for lock 1 first. So there are many ways kind of implementing this one. For example, inode. So we inode is file metadata. It has number. Okay, so sometimes systems need to access many files. So in case of so when you're updating the inode, you have to holding a lock for protecting inode. So the common practice for this case is that holding a lock in inode number order. So let's say I want to access inode 1, 2, 3, 4, then inode number itself is lock holding order. So you have to holding inode first inode 1's lock first, and then inode second lock, and inode third lock, and inode first lock. So you have to having a kind of sequence according to some rules. Okay. Another popular way is the virtual address. So virtual address meaning that when you declare locks always having its virtual address. So compare the virtual address and increasing or decreasing order to holding a lock. Okay, so that's kind of some popular rules to enforce this lock ordering. So this lock ordering is so important. So many kind of the deadlock detection tools profiles kind of lock holding sequence of thread A and thread B. So if there's some kind of reverse order detected, then the deadlock detector actually warn that, oh, your program in some code executions, there's a case where the lock ordering are violated, so it may cause deadlock. So this principle is popular for deadlock checkers which actually profiles lock holding order. Okay, and these are best and most common in practice. The other way is breaking the wait while holding. So to avoid this one, common approach is this atomically holding all locks. So holding a lock, so when you are executing the thread, you holding a lock at some point, and then later, after executing some code and holding a lock later, so you want to make this hold operation atomically. How? You need to introduce new lock, which is kind of, you can say meta lock. This is lock for holding this two lock, and then you can holding a lock internally, and after using this one, you release it. This type of locking strategy called two-phase locking. So when you're accessing the resources, the thread first holding all locks first, require lock, and then this locks log 1 to log n at the beginning, and to protect this lock hold operation atomically, so you have some kind of lock all unlock all, for example. They did this kind of outer lock to make this lock hold operation atomic, and then executing code and release locks. So two-phase locking is that make all locks, execute code, make all locks released. Okay, so in database and many complex scenario, this one effectively guarantee that when executing this code path, it profiles all the locks required and holding a lock at the first, then execute it. So the other thread trying to any lock related to any lock already held by the thread has to wait until all the lock resource. So in this approach, say lock is kind of ownership, and lock is kind of capability to access some resources. So lock first holding at the beginning, and after using the resource and release. Okay, so this strategy has known disadvantages. What is that? So first of all, to apply these techniques, you need to know all locks running this code path. So sometimes you need to profile, you have to thoroughly understand what locks require for this given code path. If you miss something, then you may kind of cause some trouble. So you have to correctly understand what kind of locks require ahead of time to executing the code. That's one thing. And most kind of, serious disadvantages of this approach is that it seriously limit the concurrency. So let's say this object only, when this lock required to access this object, but you holding a lock at the beginning. So the best way to guarantee the concurrency is that holding a lock at the time it required. But in this approach is conservative, so that you have to holding a lock at the first time, so it limit the concurrency for code. So it's impacts on performance. But it works. So when things are very complicated, this two-phase locking is known technique, especially in the database applications. And the last thing, last way to avoid deadlock is avoiding no preemption. So this strategy is basically make a lock preemptive. So it requires a new type of lock called try lock. Try lock is try to holding lock several times. If it fails, then try lock returns error. So try lock like this one. You first holding a lock at the beginning, say, and then to acquire resource, you need to try the second lock, and then this lock is tried. So if you fail to acquire lock, then you have to release the lock and goes to again and try holding a lock again. So after that, you are voluntarily preempt. Okay, preempt resource so that it actually break the condition, deadlock condition of no preemption. What are disadvantages of these approaches? Can you guys guess what is the disadvantage of this try lock approaches? What is it? Sometimes this try lock does not make a progress. So always trying to holding a lock, but try lock fails, release, go again. And holding a lock fails, release resource, go again. So this loop goes infinite. So it causes starvation. So technically, this no preemption violation using breaking the no preemption with try lock does not guarantee the progress. So it causes starvation problem. Right, so these are 3 common techniques to avoiding deadlock. And the next topic we discuss is deadlock recovery. Deadlock recovery is when deadlock happens and there is some kind of remedy, recovery action to break the deadlock. Likewise, deadlock recovery break the 3 deadlock conditions, but not magic. There's not magic in the recovery logic. So common approach is to abort the process. So the wafer condition causing kind of the wafer the circular cycle. So if the operating system aborts a process firstly, then it breaks the cycles so that make the system can hoping that system can progress. So this does not guarantee always deadlock is resolved. So even if one process is terminated, the other process make holding a cycles to causing a deadlock. But this is kind of optimistic approach where you can kill the one process. The other one is to abort all process. This is pretty inefficient, but sometimes it works. So all the process are killed and restart the process to hoping that deadlock never happens again. Likewise, this deadlock recovery mechanism is optimistic. There's no formal guarantee that deadlock would not happen. The other one is more fine-grained approach where it can preempt only certain resources, certain locks. So when process holding a lock, operating system randomly select a process and release the falsely released lock. Of course, to release the lock, it requires some kind of a way to roll back process previous states before holding a lock, and need a way to prevent starvation. Okay, so usually the transaction is having supporting this kind of approach, but again, this is also optimistic. So after do this recovery, deadlock may or not happen. Okay, so these are two approaches for deadlock recovery. So beware that key things I want to emphasize for this one is three important deadlock conditions: circular waiting, and wait for holding, and no preemption. Circular waiting is most common in practice. So good programming practice is always enforce lock holding order, either some kind of numbering scheme or some virtual address. You need to holding a lock in a specific order in every thread. All right, so that's about deadlock, and let's talk about non-deadlock bugs. So non-deadlock bugs has two common patterns. There are lots of complicated bug patterns, non-deadlock patterns, but 97% of non-deadlock bug belongs to these two patterns. I'm just kind of briefly into these two patterns, but if you are really understand details of deadlock, I recommend to reading this great paper. So this is paper about in concurrency programming, where you can actually analyze many bug patterns in real world application. I recommend to look at. So this paper pointing out these two common patterns. Let's take a look at the patterns. The first one, the popular order violation. Atomicity violation. So atomicity violation is that when there are one statement and two statements, they are accessing shared states. So thread proc_info read reading these two statements. So correct semantic is that when this proc_info is not null, and you can access proc_info. So this value and this value has to be identical. So but in some thread interleaving, so in some thread execution cause that after executing this thread and these two threads are free, this proc_info and set null, and then access it again. So at the time when statement S1 reading this value, at the time statement S2 reading this value are different. So atomicity is violated. To prevent atomicity violation, what's the way? How to make this statement S1, S2 are executed atomically? Simple way, right? We run this mechanism, lock. So order violation usually happens when you have to put the lock, but you forget. So this causes atomicity violation. Common pattern is that one variable, one reader, one writer, one reader. So read and this read are inconsistent, not atomic. Okay, so to avoid this atomicity violation, the atomic read or atomic update operation has to be protected by lock. Okay. The other condition is called order violation. So order violation, you have to assume that some specific program execution order. So for example, when thread 1 create a thread, and this thread variable having a kind of thread identifier is allocated, then after that the thread this thread 2 can access this mthread struct identifier to access state. So has some value. The correct sequence of order is this one. Okay. However, there are some cases where thread 2 execute the first and thread 1 execute later. So thread 1 execute first before locating the thread causing violation. Okay. So to avoid this one, if you put the lock here, and if you put the unlock here, like a attempted violation case, if you put the lock here, unlock here, say, does this solution work? Is this if you're protecting these two threads with the lock, does it solve this order violation problem? How do you think? No, right? So having a lock, protecting this thread with the lock only guarantee the atomic operation, but does not talking about anything for ordering of these two threads. So we learn some primitives to enforce specific ordering. So always make the ordering happen. Always happen this first and take this statement later. So what primitives require for this guarantee? What was that? Conditional variable. Okay. So this order violation is a specific case where you miss using the conditional variable to enforce ordering. This two pattern looks very simple, but surprisingly, all the complex bugs categorize these two things: order violation, thread 1, thread 2. So these are two inconsistent results, and thread 1 must happen before 2. But some buggy pattern caused thread 1, thread 2. So these are two common patterns. If you have some kind of encounter concurrency bugs, you first think about these two patterns. Well, whether my problem happens this order violation or atomic violation, and you have to kind of find a clue to reason about your concurrency bug. Surprisingly, these two simple patterns explain most of concurrency bugs. All right, so that's all for concurrency bugs. And if you have any questions, feel free to ask your questions to Piazza. Thank you.